Thank you for setting me up with such a wonderful thing to follow up. But I think he's said all the good stories. It'll be much easier for me because he's motivated more than everything I'll ever get to. Lots of collaborators, just the prominent ones named here. Okay. Modeling, data processing, analysis, scientific machine learning, AI. The purpose of all this is insight and hopefully prediction. Prediction, of course, is the grand game. Been at it for about 3,000 years. Still working on it. Whether you take some interesting substances to predict better, or you use HPC, now quantum, causal. Game hasn't changed. Life gets always a little more interesting. We do good things on the computer, then life does something else. We have models, we have submodels, we have to put them together. Data's got to communicate, the data's got to be good. Resolution, super resolution. Do you have enough data? Of course, the data doesn't come nicely ever. Any problem that somebody wanted to give me money for had to be bloody painful. For once in life, give me money for an easy problem, please. No. Data's got error, uncertainty, and you never have enough of it. And of course, after all that, you got to put it all together. Computers, networks, people. So I'll talk a little bit about, we have a small amount of time, so a few vignettes on each of these three questions. Then I'll finish up with an interesting insight from somebody much smarter than me. Two problems that I want to kind of use. We have done agriculture, we have done all kinds of other things, but I'll send you off to space. A hybrid rocket motor. Now, we keep blowing them up every 3-4 days. Hybrid rocket motors are basically paraffin, stuff you see in candles, which apparently has the caloric value. If you can burn the thing fast enough and correctly, it's going to be a very safe rocket. And a bunch of very smart people at Stanford and NASA have been quietly doing a garage thing on this. I didn't know all about this. And they've come pretty close. So we had some DOE money to look at this with my very smart propulsion man leading the charge. On the top picture there is a NASA rocket that NASA fired off a couple of these in a wind tunnel in stationary configuration. At the bottom, and I'll show you more details, we're just trying to understand how does paraffin burn. It liquefies and then it atomizes and then burns. As you can quickly guess, the physics, the chemistry, the fluids, the turbulence, okay, I could go on. And the most interesting thing I discovered was hydrocarbon chemistry of combustion above about octane is barely understood. Simply because aircraft burn octane, that's all the Air Force would pay for. Nobody else wanted to look at that. We started looking at it. The second one is a problem that variations of which I've been working on for 2 or 3 decades now. Land masses, landslides, in this case, post-fire debris flows. If it hasn't happened today, it'll probably happen tomorrow. Not so much around here, but if you end up in California, stay in high ground. Anyway, so those are the two problems I want to talk about. But things that I want to keep in mind, there are certain absolutes that over hundreds of years we have learned, conservation laws. Then there are things that we have to close. How does paraffin burn? We don't know, but energy is conserved. How does the landmass, how does soil get mobilized on a surface? Very hard to tell. There's grass, there's how fast is the water, how fast is, how many rocks are there, but the total mass is conserved. So we have to take advantage of these few golden truths we have, which already are causal in many senses of the term. And then we got to layer in all these other things. Okay, so that's not supposed to go into all the details of it. I will not. But all I wanted to show you is that all the models and submodels that go into that paraffin combustion problem. Okay? You're looking at the chemistry of the combustion itself, which can be up to 50, 60 species, even more. We do a fairly simplified version of it. There's activation constants and things like that involved with every single one of them. Some of them we find the most sensitive ones, and that's the top 2 or 3 is what we can play with. Then during the combustion process, and you see in the middle of the thing is that little piece of slab of wax about 2 inches long that we have burned so far to study all this detail. And see how much goes into that. The flow surrogates, the flows are complex 3D Navier-Stokes simulations, which on the previous one, not on Lassen, should take days. So the idea that we can run very large ensembles to understand every scenario is not possible. But so we build good flow surrogates. The chemistry requires tons of parameters, and this is where in a very interesting application of machine learning is coming in. You cannot understand every single one of them, but you can run a lot of simple flames, learn that into a nice deep learning model, and in real time try to get this. The flow simulation queries, okay, if I have this, is this a flame? What kind of characteristics of the flame do I get here? So this is all pretty smart if it all comes together. Then, of course, the atomization and liquefaction, again, the process is very complicated, takes tons and tons of supercomputing, but to run it real time inside this flow simulator, that's another thing where you have to simplify and represent. So we have a general strategy in some sense, characterize the data and model uncertainty, use ensembles of simulation as a representation of all the possibilities, and then with some smart putting it all together, hopefully good things happen. Of course, surrogates are not easy. Surrogates we've been building them for a while. We still needed a new one for the turbulent combustion, for this thing. Regression rate of the paraffin, and you can see that the uncertainty has been propagated successfully. Here's a couple other problems where when I first started post-grad school, in grad school, data was not the problem. The problem was how do I evaluate the model? How do I parallelize everything and solve Navier-Stokes or whatever? Turns out data is a problem. On the bottom, on the top left there is a problem we have played with for some time. I won't talk about much today, but as an exemplar of how interesting data can be, this is remote sensing data from the ICESat, somewhat similar to the satellite remote sensing data. So you get these tracks, and you have to reconstruct the surface of entire Greenland, entire Antarctica, from tracks that may be 90 days or even longer apart. Of course, to evaluate how much ice mass you have lost, you have to evaluate that surface perfectly. Yes, right, that's happening. Almost made me a climate skeptic for some time. But regardless, we've done some very interesting work on putting that surface together based on trying to do some very classical statistical learning of this thing and interpolation. On the bottom there, the temperature fields. This is just taking lots of imagery and reconstructing with what they call pyrometry. Again, putting 3 signals together, looking at their uncertainties, reconstructing the temperature field. On the right, what we thought would be the simplest thing, piece of wax burning, let's just get the surface, right? Well, the wax splatters and this and that. The high-speed camera does not have the frame rates and so on. So again, a very detailed CNN-type model we had to use to reconstruct just the surface of it. So data is interesting. Data needs the most work because that's the beginning of the pipeline. This is our our landslide problem again. So getting back to this one, you want to have some kind of a probabilistic estimate. When is the flow going to hit a point so you can get people to go away? I don't know if anybody watched the news. But Valencia, I think people are suing the emergency managers because they didn't get warned about a debris flow which killed a bunch of people. And it should have been predictable. So we're trying to do that, have essentially real-time prediction, lots of simulations, feed that in, create probabilistic scenarios. Now, of course, our wonderful surrogate here, based on deep learning with CNN and so on, works quite well. and you can actually get a probability map. There's only one problem here. I only have data for where things have happened. I have analyzed 15 mountains, and of course, nature does not cooperate. The real problem will be the one that I have not seen before. So how do I go with what I know to this new place? How do I predict based on existing knowledge to new ones? And human beings, smart as they are pretty darn good at this. Somehow they know how to extrapolate better than most of us. That's the game. We are all trained, machines or people, and we have to figure out how to predict beyond what we know. Sometimes we'll be right, sometimes we'll be wrong. If we're right more often than we're wrong, I think we win. Of course, if you're a doctor, you better be right every time, especially when you're looking at me. So some problems are very critical that we can maybe afford 1 in a million mistakes. Some 1 in 5. In this particular 2 problems I've told you, of course, these are more the 1 in a million kind. But do we have enough data ever for extrapolation? By definition, not. By definition, not. So what do I do? All models, of course, are interpolative. How do I know which model is extrapolative? So this landslide problem gave us a very interesting insight. We haven't figured out how to generalize it quite well yet, but we figured something out here, which I think may be very helpful. Because in this problem especially, the rainfall has a certain distribution that's essentially transferable. Okay? The topography is not. Every mountain is unique. So that's what I need to understand. So if I have trained on 5 mountains, how do I know that my 6th mountain is adequate? That my model is good enough for that. So what of course, we tried with our little CNN-based model, and sometimes if you just take it to a new mountain, it works perfectly. Sometimes it does not. So thinking about that, what we have discovered is that if you can answer the following question in a proper measure of your training set, that is the summum of your knowledge. Whatever algorithm you used, everything came from that. If your prediction scenario is in the training manifold, loosely speaking, may not mathematically be a manifold, you're good. Question, of course, is how do I know that? I don't, easily. So this is where I have to figure out measure of distance of my prediction scenario, 2 minutes. I should be done in 1. And that is where we've discovered some very interesting engineering tricks. This is where science starts, solve a problem. We discovered that we could do a couple things long back. I had this notion that these topographies are too painful. Is there a way I can cluster them and make them simple and so on? We learned that spectral clustering, very classical spectral clustering, is extremely good at classifying topography. Spectral clustering based on an interesting mix of slopes and elevations, which is custom. So we did that. So now we have 5 or 6 bins. If I have 5 or 6 bins, the quote-unquote theoretically impossible to evaluate optimal transport distances are easy to evaluate. So in real time, more or less, I can evaluate this synchron distances. And amazingly, if the synchron distances between the the testing mountain and the training mountains, not mountain, all the 5 and this is small, guess what? My model works. Beautiful. And then if I do the following, I add where it does not work, I learn a few more things. I add a few more. And guess what? It keeps getting better and better. So depending on how far my testing is from the training stuff, I need more and more or less. But guess what? I can now answer that question before I predict if my model is qualified to predict. Okay. I am going to more or less stop at this. I had one more part here where I was going to talk about trying to predict wait times as we start putting these things together. We've been collecting Exceed network data for 15 years now. So we can actually predict wait times so we can figure out how to put it all together in a workflow. It was here somewhere. We can talk later. But the final goal is that we can tell you, yes, this is a good model to run, now go run it there. Okay? And anyway, so integrate real-time data, knowledge, computing, everything into this nice little vision. It's going to take some interesting ways of thinking about prediction, about insight. Causal was awesome. I'll leave you some famous words from two people, two very smart people. The older one, Automation of Reasoning Thinking. If any of you have not read this article, please go read it once every 5 years. Mr. Bush pretty much had it. All we have to do is execute his vision. And of course, a more recent one about data science and so on, which justifies my salary. Thank you very much.